Industrial designs. Ideas and inventive problem solving for industrial design. Written by Phil Gilbert. Narrated by Kevin Brooker. Part 1. Introduction. 1.1. The role of industrial design in modern industry. Industrial design plays a pivotal role in modern industry by significantly influencing product functionality, aesthetics, user experience, and market competitiveness. One of the primary contributions of industrial design is the enhancement of product functionality and usability. Designers achieve this by thoroughly understanding user needs and behaviors, which allows them to create products that are intuitive and easy to use. This not only boosts customer satisfaction, but also reduces the demand for customer support. The aesthetic appeal and brand identity of a product are also heavily shaped by industrial design. A well-designed product can greatly enhance a brand's image and market position, as the integration of form and function results in visually appealing products that stand out. This visual attractiveness is a critical factor in consumer decision-making and fostering brand loyalty. Innovation and differentiation are crucial in a competitive market, and industrial designers play a key role here by merging creative thinking with technical expertise. This fusion leads to the development of unique features and functionalities that distinguish products from those of competitors. Cost efficiency and sustainability are other vital aspects influenced by industrial design. Designers strive to optimize material usage and production methods, reducing costs and increasing profitability. Additionally, the growing emphasis on sustainability has led designers to focus on creating eco-friendly products that minimize environmental impact. User experience is greatly enhanced by industrial design, as it ensures products are not only functional, but also comfortable and safe to use. Ergonomic considerations are paramount, reducing user fatigue and injury, which ultimately leads to a better overall user experience. The integration of technology into products is another significant aspect of modern industrial design. Designers incorporate smart features, connectivity, and automation, thereby enhancing product capabilities and user interaction. Moreover, industrial designers help companies remain responsive to market trends and consumer demands. By staying informed about technological advancements and societal shifts, designers enable companies to adapt their products to meet changing needs and preferences. In conclusion, industrial design is integral to modern industry, providing a strategic advantage through improved product functionality, user experience, and brand differentiation. As markets evolve and consumer expectations rise, the role of industrial design becomes increasingly critical in driving innovation, sustainability, and market success. 1.2. Overview of industrial design processes. The industrial design process is a systematic approach used to develop new products, ensuring they meet user needs, are aesthetically pleasing, functional, and marketable. It begins with extensive research and analysis to understand the market, user needs, and existing products. This involves gathering information about potential users, their behaviors, and preferences through surveys, interviews, and observations. Competitive analysis helps identify gaps in the market and opportunities for innovation. Based on the insights gained from the research, designers then brainstorm and generate multiple ideas and concepts. This stage is highly creative, involving sketching, creating mood boards, and conceptualizing different solutions. The goal is to explore a wide range of possibilities and select the most promising concepts of further development. The selected concepts are refined and developed into more detailed designs, which involves creating detailed sketches, 3D models, and prototypes. Designers focus on the form, function, and ergonomics of the product, ensuring it meets both user needs and manufacturing requirements. Computer-aided design, or CAD software, is often used at this stage to create precise models and simulations. Next, prototypes of the product are built to test and validate the design. These prototypes can be physical models or virtual simulations. Testing involves evaluating the product's functionality, usability, and durability. Feedback from users and stakeholders is collected and analyzed to identify any necessary improvements or adjustments. Once the design has been thoroughly tested and refined, the final design is developed. This stage involves detailing all aspects of the product, including materials, finishes, colors, and manufacturing processes. Detailed technical drawings and specifications are created to guide the production process. The final design is then handed over to the manufacturing team for production. Designers work closely with engineers and manufacturers to ensure the product is produced accurately and efficiently. This may involve selecting suppliers, overseeing the production process, and conducting quality control checks. After production, the product is launched into the market. This stage involves marketing, distribution, and sales. Designers may continue to be involved in monitoring the product's performance in the market, gathering feedback, and making any necessary adjustments or improvements based on user responses and market trends. The industrial design process is a comprehensive and iterative approach that involves multiple stages, each critical to the development of a successful product. From initial research and concept development to prototyping, testing, and final production, each step ensures the product meets user needs, is functional, aesthetically appealing, and competitive in the market. By following this structured process, industrial designers can create innovative and high-quality products that meet the demands of modern consumers and markets. Part 2. Fundamentals of Industrial Design. 2.1. History and Evolution of Industrial Design. The history and evolution of industrial design is a journey that reflects the transformation of society, technology, and industry from the early days of the Industrial Revolution to the present. Early beginnings. The Industrial Revolution. The roots of industrial design can be traced back to the Industrial Revolution in the late 18th and early 19th centuries. During this period, the rise of mechanized production led to a dramatic increase in the availability and variety of goods. However, these early products were often more functional than aesthetically pleasing. The focus was on manufacturing efficiency rather than user experience or design. The arts and crafts movement. In the mid-19th century, the arts and crafts movement emerged as a reaction against the mass production and poor quality of industrial goods. Led by figures like William Morris in Britain, the movement emphasized craftsmanship, quality materials, and the aesthetic value of everyday objects. This period marked the beginning of a more conscious effort to integrate design with industrial production. The birth of modern industrial design. The early 20th century saw the birth of modern industrial design as a distinct profession. Influential schools and movements such as the German Bauhaus and the American Streamline Modern played a crucial role in shaping the field. The Bauhaus, founded in 1919 by Walter Gropius, promoted the idea that form should follow function and that good design should be accessible to all. This philosophy led to the creation of products that were both functional and visually appealing. The impact of World War II. World War II had a significant impact on industrial design. The need for efficient, mass-produced goods for the war effort accelerated technological advancements and manufacturing techniques. Designers like Raymond Loewy and Henry Dreyfuss in the United States became prominent figures, creating iconic designs that combined functionality with a streamlined modern aesthetic. Post-war boom and consumer culture. The post-war era of the 1950s and 1960s was marked by economic prosperity and the rise of consumer culture. Industrial design flourished as companies sought to create attractive, desirable products to fuel consumer demand. This period saw the introduction of new materials, such as plastics, and innovative manufacturing processes. Designers like Charles and Ray Eames, known for their furniture designs, became household names. The Digital Revolution. The late 20th and early 21st centuries brought about the digital revolution, fundamentally changing the landscape of industrial design. The advent of computers, digital modeling, and new manufacturing technologies, such as 3D printing, allowed designers to create more complex and precise products. The integration of technology into everyday objects became a central theme, leading to the development of smart products and user-centered design. Sustainability and social responsibility. In recent decades, there has been a growing emphasis on sustainability and social responsibility in industrial design. Designers are increasingly focused on creating products that minimize environmental impact, use sustainable materials, and promote ethical production practices. This shift reflects a broader awareness of the need to balance economic growth with environmental stewardship and social equity. The history and evolution of industrial design is a testament to the dynamic interplay between technology, society, and industry. From the mechanized production of the Industrial Revolution to the digital innovations of the 21st century, industrial design has continually adapted to meet the changing needs and values of society. Today, it remains a vital field that shapes the way we live, work, and interact with the world around us. 2.2 Key Principles of Industrial Design. The key principles of industrial design serve as foundational guidelines that help designers create products that are functional, aesthetically pleasing, user-friendly, and sustainable. These principles ensure that the design process leads to products that effectively meet user needs and enhance the overall experience. Here are the core principles. 1. Functionality. Functionality is paramount in industrial design. A product must effectively perform its intended purpose. This means considering how the product will be used and ensuring that it operates efficiently and reliably. Designers must focus on user needs and the practical aspects of how a product works. 2. Aesthetics. The visual appeal of a product is crucial for attracting users and creating a positive first impression. Aesthetics can encompass the product's form, color, texture, and overall visual language. Good design harmonizes these elements to create products that are not only functional, but also beautiful and pleasing to look at. 3. Ergonomics. Ergonomics involves designing products that are comfortable and easy to use. This principle ensures that products fit the human body and its movements, reducing strain and enhancing usability. Ergonomic design considers factors such as size, shape, weight, and the placement of controls. 4. User-centered design. User-centered design places the user at the forefront of the design process. This principle involves understanding user needs, preferences, and behaviors through research and user testing. Designers create products that are intuitive and easy to use, ensuring a seamless interaction between the user and the product. 5. Simplicity. Simplicity in design means creating products that are straightforward and easy to understand. It involves minimizing complexity and avoiding unnecessary features. Simple designs are often more user-friendly and can lead to better user experiences by reducing confusion and enhancing clarity. 6. Sustainability. Sustainability is an increasingly important principle in industrial design. Designers are encouraged to consider the environmental impact of their products throughout the entire life cycle, from material selection and production to use and disposal. Sustainable design practices include using eco-friendly materials, reducing waste, and creating products that are durable and recyclable. 7. Innovation. Innovation is at the heart of industrial design, driving the creation of new and improved products. This principle involves exploring new ideas, technologies, and materials to solve problems in novel ways. Innovative design can lead to products that offer unique features, improved performance, and enhanced user experiences. 8. Feasibility. Feasibility ensures that a product can be realistically manufactured and brought to the market. Designers must consider production methods, costs, and technical constraints. This principle involves collaborating with engineers and manufacturers to ensure that designs are practical and viable within the given limitations. 9. Durability. Durability focuses on creating products that are long-lasting and robust. This principle involves selecting materials and construction methods that ensure the product can withstand regular use and environmental conditions. Durable designs contribute to sustainability by reducing the need for frequent replacements. 10. Safety. Safety is a critical consideration in industrial design. Products must be designed to prevent accidents and injuries during use. This involves identifying potential hazards and incorporating safety features to protect users. Safety standards and regulations must be adhered to throughout the design process. The key principles of industrial design, functionality, aesthetics, ergonomics, user-centered design, simplicity, sustainability, innovation, feasibility, durability, and safety provide a comprehensive framework for creating successful products. By adhering to these principles, designers can ensure that their products are not only effective and appealing, but also socially and environmentally responsible. These principles help guide the design process, leading to products that enhance the quality of life and contribute positively to society. 2.3. The design process, from concept to production. The design process from concept to production is a structured sequence of stages that transforms an idea into a market-ready product. It begins with the initial phase of a concept development, where designers brainstorm and generate a wide range of ideas. This creative stage involves sketching, creating mood boards, and conceptualizing different solutions to explore various possibilities. The objective is to identify the most promising concepts that address user needs and market demands. Following the concept development, the process moves into the research and analysis stage. Designers conduct thorough research to understand the target market, user behaviors, and existing products. This research includes user surveys, interviews, and competitive analysis to gather valuable insights that inform the design direction. The goal is to uncover user needs and preferences, as well as identify opportunities for innovation. With a clear understanding of user needs and market gaps, designers enter the design refinement stage. Here, the selected concepts are developed into more detailed designs. This involves creating detailed sketches, 3D models, and prototypes to visualize the product. Designers focus on the form, function, and ergonomics, ensuring that the product is not only aesthetically pleasing, but also practical and comfortable to use. Computer-aided design, or CAD software, is often utilized to create precise models and simulations. The next stage is prototyping and testing, where physical or virtual prototypes are built to test and validate the design. Prototyping allows designers to evaluate the product's functionality, usability, and durability. During testing, feedback from users and stakeholders is collected and analyzed to identify any necessary improvements or adjustments. This iterative process of testing and refining ensures that the design meets the desired standards and user expectations. Once the design has been thoroughly tested and refined, it moves into the final design and detailing stage. In this phase, all aspects of the product are meticulously detailed, including materials, finishes, colors, and manufacturing processes. Detailed technical drawings and specifications are created to guide the production process. Designers work closely with engineers to ensure that the design can be manufactured accurately and efficiently. The production and implementation stage follows, where the final design is handed over to the manufacturing team. Designers collaborate with manufacturers to oversee the production process, ensuring that the product is produced to the required quality standards. This may involve selecting suppliers, managing production timelines, and conducting quality control checks to address any issues that arise during manufacturing. The final stage is the market launch and evaluation. After production, the product is introduced to the market through marketing, distribution, and sales efforts. Designers may continue to monitor the product's performance, gathering feedback from users and analyzing market response. This ongoing evaluation helps identify any areas for improvement and informs future design projects. In summary, the design process from concept to production involves a series of interconnected stages: concept development, research and analysis, design refinement, prototyping and testing, final design and detailing, production and implementation, and market launch and evaluation. Each stage is crucial in ensuring that the final product is functional, aesthetically pleasing, user-friendly, and marketable. Through this structured process, designers can create innovative and high-quality products that meet the needs of modern consumers and markets. Part 3: Ideation and Concept Development. 3.1 Techniques for Generating Ideas. Generating ideas is a crucial step in the design process, and there are several techniques that designers use to stimulate creativity and innovation. These techniques help in exploring a wide range of possibilities and identifying the best solutions to design challenges. Sketching and doodling are fundamental techniques for visualizing ideas quickly and effectively. By putting ideas on paper, designers can explore different concepts, experiment with forms, and communicate their thoughts more clearly. Sketching allows for rapid iteration and refinement of ideas, making it easier to develop and evaluate multiple concepts. Scamper is a structured approach to idea generation that stands for substitute, combine, adapt, modify, put to another use, eliminate, and reverse. This technique encourages designers to think about how they can change existing products or ideas to create new solutions. By systematically considering these different actions, designers can generate a wide range of innovative ideas. Role-playing involves putting oneself in the shoes of the end user to better understand their needs and experiences. By stimulating how a user would interact with a product or service, designers can gain insights into potential improvements and new features. This empathetic approach helps in generating ideas that are user-centered and relevant. Reverse thinking is a technique where designers start with the desired outcome and work backward to figure out how to achieve it. This approach can help in identifying new strategies and solutions that might not be obvious when thinking in a linear, forward-thinking manner. Analogies and metaphors are used to draw parallels between a design problem and unrelated concepts or objects. By comparing the design challenge to something familiar, designers can gain new perspectives and insights. This technique often leads to creative breakthroughs by highlighting similarities and differences that inspire innovative ideas. Collaboration and co-creation involve working with other designers, stakeholders, or even end users to generate ideas collectively. This collaborative approach leverages diverse perspectives and expertise, leading to richer and more varied ideas. Co-creation sessions can include workshops, focus groups, and collaborative brainstorming sessions. The 6 thinking hats technique, developed by Edward de Bono, involves looking at a problem from 6 different perspectives, each represented by a different hat. White, facts and information. Red, feelings and intuition. Black, critical judgment. Yellow, positive thinking. Green, creativity. And blue, process control. This structured approach ensures a comprehensive exploration of ideas from multiple angles. Trend analysis involves studying current trends and emerging patterns in the market, technology, and society. By understanding these trends, designers can generate ideas that are relevant and forward-thinking. This technique helps in identifying opportunities for innovation and staying ahead of the curve. In summary, techniques for generating ideas include brainstorming, mind mapping, sketching and doodling, scamper, role-playing, reverse thinking, analogies and metaphors, collaboration and co-creation, the 6 thinking hats, and trend analysis. These techniques provide a structured and diverse approach to creativity, helping designers explore a wide range of possibilities and develop innovative solutions to design challenges. 3.2. Brainstorming and mind mapping. Brainstorming and mind mapping are two effective techniques for generating and organizing ideas during the design process. They each have distinct methods and applications, but can be used together to enhance creativity and problem solving. Brainstorming. Brainstorming is a group activity designed to generate a large number of ideas quickly. The goal is to create an open, uninhibited environment where participants feel free to share their thoughts without fear of criticism. Here's how it typically works. 1. Define the problem. Clearly articulate the problem or challenge that needs to be addressed. This ensures everyone is focused on the same issue. 2. Gather a diverse group. Include people with different perspectives and expertise to enrich the idea pool. 3. Set ground rules. Emphasize that all ideas are welcome. There should be no criticism or judgment, and quantity over quality is encouraged initially. 4. Generate ideas. Encourage participants to share as many ideas as possible, building on each other's suggestions. This phase is usually timed to keep the energy high and ideas flowing. 5. Record ideas. Write down every idea on a whiteboard, sticky notes, or digital tools so they can be reviewed and organized later. 6. Evaluate and refine. After the brainstorming session, review the ideas, group similar ones, and evaluate their feasibility and potential. Brainstorming helps in unlocking creativity, promoting collaborative thinking, and uncovering a wide range of solutions that might not be immediately apparent. Mind mapping. Mind mapping is a visual technique used to organize and structure ideas, making it easier to see connections and relationships between them. Here's how to create a mind map. 1. Start with a central idea. Write the main topic or problem in the center of a blank page or digital canvas. 2. Branch out. From the central idea, draw branches to subtopics or related concepts. These branches represent major categories or components of the central idea. 3. Add details. For each subtopic, add further branches to include more specific details, examples, or related ideas. Continue breaking down complex ideas into simpler, more manageable parts. 4. Use keywords and images. Use single keywords or short phrases to represent ideas. Incorporate images, symbols, and colors to make the mind map more engaging and easier to understand. 5. Show connections. Draw lines or arrows to indicate relationships and connections between different ideas or subtopics. Mind mapping helps in organizing complex information, visualizing the structure of ideas, and discovering new connections and patterns. It's particularly useful for breaking down large problems into smaller, more manageable parts and seeing the big picture. Combining brainstorming and mind mapping. These two techniques can be used together effectively. After a brainstorming session, you can use mind mapping to organize and refine the generated ideas. Here's how. 1. Brainstorm ideas. Conduct a brainstorming session to generate a wide range of ideas related to your design challenge. 2. Group and categorize. Once you have a list of ideas, use mind mapping to group similar ideas and categorize them into subtopics. 3. Visualize connections. Create a mind map that visually represents the relationships between different ideas, helping you to see patterns and connections. 4. Refine and expand. Use the mind map to identify gaps, refine ideas, and expand on promising concepts. By combining brainstorming and mind mapping, you can harness the power of group creativity while organizing and structuring ideas in a clear and visual manner. This integrated approach enhances problem solving and innovation, leading to more effective and creative design solutions. 3.3. Sketching and conceptualization. Sketching and conceptualization are fundamental stages in the design process, serving to translate abstract ideas into tangible concepts. Sketching enables designers to quickly visualize ideas, explore various design possibilities, and communicate concepts visually. It allows for rapid iteration where multiple sketches are created to investigate different aspects of the design problem. Sketches serve as a means of communication, conveying ideas to team members, clients, and stakeholders more effectively than verbal descriptions alone. Through sketching, designers can identify potential issues early on and develop solutions that are both functional and aesthetically pleasing. As ideas evolve, initial rough sketches can be refined into more detailed drawings, facilitating the fine-tuning of the design and the incorporation of specific details. Conceptualization involves refining and developing initial ideas generated through sketching into more defined and coherent concepts. This stage is critical for shaping the overall vision of the design. Designers review and select promising sketches, refining them into detailed concepts. Physical or digital models may be created to explore the form and function of the design in more depth. Concepts are shared with stakeholders to gather feedback, which is used to refine the ideas through iterative development. The final concepts are presented in a polished form, using detailed sketches, renderings, and models to communicate the design intent effectively. The combination of sketching and conceptualization is a powerful approach in the design process. Initial exploration begins with loose, quick sketches to generate as many ideas as possible. Promising sketches are then developed into refined concepts, using detailed drawings and models to explore form, function, and aesthetics. Feedback from stakeholders informs further iteration until a final concept is achieved. In summary, sketching and conceptualization facilitate creativity, problem solving, and effective communication in the design process, leading to successful design outcomes. 3.4. Design thinking in industrial design. Design thinking in industrial design is a human-centered approach that places the needs and experiences of users at the forefront of the design process. It involves a systematic and collaborative approach to problem solving, emphasizing empathy, creativity, and iterative prototyping. Here's how design thinking is applied in industrial design. Empathize. The first stage of design thinking involves empathizing with the end users to gain a deep understanding of their needs, preferences, and challenges. Industrial designers engage in user research, observation, and interviews to develop empathy and insights into the user's perspective. By understanding the user's context and motivations, designers can identify opportunities for innovation and design solutions that truly address user needs. Define. In the define stage, designers synthesize the information gathered during the empathize stage to define the problem statement and design challenges. This involves reframing insights into actionable design opportunities and establishing clear design criteria. By defining the problem space, designers ensure that they are addressing the right problem and setting the foundation for creative ideation. Ideate. During the ideation stage, designers generate a wide range of ideas and potential solutions to address the defined design challenges. This is a brainstorming phase where creativity is encouraged and no idea is too far-fetched. Designers use techniques such as brainstorming, mind mapping, and sketching to explore different concepts and possibilities. The goal is to generate as many ideas as possible and explore diverse approaches to problem solving. Prototype. In the prototype stage, designers create tangible representations of their ideas to test and iterate on. Prototypes can range from simple sketches and mock-ups to more sophisticated 3D models and prototypes. The focus is on creating low-fidelity prototypes quickly and iteratively to gather feedback and refine the design. Prototyping allows designers to explore different concepts, evaluate their feasibility, and identify areas for improvement. Test. The final stage of the design thinking involves testing prototypes with end users to gather feedback and validate design decisions. Designers observe how users interact with the prototypes, gather feedback through interviews and surveys, and identify areas for refinement. Testing is an iterative process where designers cycle back to previous stages to make adjustments based on user feedback. The goal is to ensure that the final design meets user needs and expectations effectively. By following the principles of design thinking, industrial designers can create products that are not only functional and aesthetically pleasing, but also truly meaningful and impactful for users. Design thinking fosters innovation, collaboration, and user centricity, enabling designers to develop solutions that address real-world problems and enhance people's lives. Part 4. Materials and Manufacturing Processes. 4.1. Understanding materials, metals, plastics, composites, and more. Understanding materials is essential in industrial design, as different materials offer unique properties and characteristics that influence product design and manufacturing processes. Here's an overview of some common materials used in industrial design. Metals. Metals are widely used in industrial design due to their strength, durability, and versatility. Common metals used in design include steel. Known for its strength and durability, steel is commonly used in structural components and consumer products. Aluminum. Lightweight and corrosion resistant, aluminum is often used in automotive, aerospace, and consumer electronics. Brass. Brass offers a unique aesthetic appeal with its golden hue and is commonly used in decorative elements and hardware. Copper. Prized for its conductivity and malleability, copper is used in electrical wiring, plumbing, and decorative applications. Plastics. Plastics are popular in industrial design due to their versatility, low cost, and ease of molding. Common types of plastics include polyethylene or PE, used in packaging, containers, and household products. Polypropylene or PP. Known for its toughness and heat resistance, PP is used in automotive parts, medical devices, and consumer products. Polycarbonate, PC, offers high impact resistance and transparency, making it suitable for eyewear, electronic enclosures, and safety equipment. Acrylic or PMMA. Prized for its optical clarity and weather resistance, acrylic is used in signage, display cases, and lighting fixtures. Composites. Composites are materials made from two or more constituent materials with different properties. Common types of composites include fiber reinforced polymers or FRP. Composites made from a polymer matrix reinforced with fibers such as carbon fiber or fiberglass. FRPs are lightweight and strong, making them ideal for aerospace, automotive, and sporting goods. Natural fiber composites. Composites made from natural fibers such as wood, bamboo, or hemp embedded in a polymer matrix. These materials offer environmental benefits and are used in furniture, construction, and automotive interiors. Ceramics. Ceramics are hard, brittle materials made by firing clay or other non-metallic minerals at high temperatures. Common ceramics used in design include porcelain. Known for its white, translucent appearance, porcelain is used in tableware, decorative objects, and electrical insulators. Earthenware. More porous and less durable than porcelain, earthenware is used in pottery, tiles, and decorative items. Stoneware. Fired at higher temperatures than earthenware, stoneware is durable and suitable for tableware, cookware, and decorative ceramics. Wood. Wood is a natural material prized for its warmth, texture, and aesthetic appeal. Common types of wood used in design include hardwoods, such as oak, maple, and walnut, are prized for their durability and rich grain patterns. Hardwoods are used in furniture, flooring, and architectural elements. Softwoods, such as pine, cedar, and fir, are more affordable and easier to work with than hardwoods. Softwoods are used in construction, cabinetry, and woodworking projects. Glass. Glass is a transparent, brittle material made by melting sand or silica and cooling it rapidly. Common types of glass used in design include soda lime glass, standard glass used in windows, bottles, and household products. Borosilicate glass, known for its high thermal resistance, borosilicate glass is used in laboratory glassware, cookware, and lighting. Tempered glass, heat treated for increased strength and safety. Tempered glass is used in windows, doors, and automotive applications. Understanding the properties and characteristics of different materials allows designers to make informed decisions about material selection, manufacturing processes, and product performance. By choosing the right materials for their designs, industrial designers can create products that are not only aesthetically pleasing, but also functional, durable, and environmentally sustainable. 4.2. Advanced manufacturing techniques. Advanced manufacturing techniques encompass a range of innovative processes and technologies that enable more efficient, precise, and flexible production of goods. These techniques represent the cutting edge of manufacturing and play a crucial role in driving innovation and competitiveness in various industries. Here are some advanced manufacturing techniques. Additive manufacturing, or 3D printing. Additive manufacturing, commonly known as 3D printing, involves building objects layer by layer using digital design data. This technique allows for the creation of complex geometries and customized products with minimal material waste. 3D printing is used in a wide range of industries, including aerospace, automotive, healthcare, and consumer goods. Computer numerical control, or CNC machining. CNC machining uses computer-controlled machines to remove material from a workpiece to create a desired shape or part. This technique offers high precision, repeatability, and versatility, making it suitable for producing complex parts with tight tolerances. CNC machining is widely used in industries such as aerospace, automotive, and electronics manufacturing. Advanced robotics. Advanced robotics involves the use of robotic systems with advanced sensors, artificial intelligence, and automation capabilities to perform tasks traditionally done by humans. Robotics enhances productivity, safety, and efficiency in manufacturing operations such as assembly, welding, and material handling. Collaborative robots, or cobots, are increasingly used to work alongside human workers in flexible manufacturing environments. Advanced materials. Advanced materials are engineered materials with superior properties and performance characteristics compared to traditional materials. Examples include carbon fiber composites, graphene, shape memory alloys, and advanced ceramics. These materials offer benefits such as lightweighting, strength, durability, and corrosion resistance, making them ideal for applications in aerospace, automotive, and renewable energy sectors. Nanotechnology. Nanotechnology involves manipulating matter at the nanoscale, 1/1000th of a meter, to create new materials, structures, and devices with unique properties and functionalities. Nanotechnology has applications in various industries, including electronics, healthcare, energy, and environmental remediation. Examples include nanomaterials for lightweight and high-strength components, nanoelectronics for faster and more energy-efficient devices, and nanomedicine for targeted drug delivery and diagnostics. Advanced simulation and modeling. Advanced simulation and modeling tools enable engineers to simulate and optimize manufacturing processes, product designs, and materials properties before physical prototypes are built. Finite element analysis, or FEA, computational fluid dynamics, or CFD, and virtual prototyping software allow for faster iteration, cost savings, and improved product performance. Internet of Things and Cyber-Physical Systems, or CPS. Internet of Things and CPS technologies connect physical manufacturing systems with digital networks, enabling real-time monitoring, control, and optimization of production processes. These technologies improve efficiency, quality, and flexibility in manufacturing operations by providing data-driven insights and predictive analytics. Examples include smart sensors, predictive maintenance systems, and digital twins of manufacturing equipment. Advanced manufacturing automation. Advanced automation systems integrate robotics, artificial intelligence, machine learning, and data analytics to automate and optimize manufacturing processes. These systems enable lights-out manufacturing, where production runs continuously with minimal human intervention. Advanced automation improves productivity, quality, and agility in manufacturing operations while reducing costs and lead times. Sustainable manufacturing. Sustainable manufacturing practices focus on minimizing environmental impact, conserving resources, and promoting social responsibility throughout the product lifecycle. Techniques such as green manufacturing, eco-design, renewable energy adoption, and circular economy principles are used to achieve sustainability goals while maintaining competitiveness and profitability. By leveraging these advanced manufacturing techniques, companies can gain a competitive edge, accelerate innovation, and meet the evolving demands of customers, markets, and regulatory requirements. Advanced manufacturing plays a critical role in driving economic growth, job creation, and sustainability in the global economy. 4.3. Sustainable materials and eco-friendly design. Sustainable materials and eco-friendly design practices are essential considerations in modern industrial design, as they promote environmental stewardship, resource efficiency, and social responsibility. Here's an overview of sustainable materials and eco-friendly design principles. Sustainable materials. Sustainable materials are sourced, produced, and used in ways that minimize environmental impact and promote long-term viability. Common sustainable materials include recycled materials. Materials that are reclaimed from post-consumer or post-industrial waste streams, such as recycled plastics, metals, glass, and paper. Renewable materials. Materials derived from natural resources that are replenished over time, such as sustainably harvested wood, bamboo, cork, and natural fibers. Biodegradable materials. Materials that can decompose naturally and return to the environment without causing harm, such as bioplastics, bio-based polymers, and organic textiles. Low-impact materials. Materials that have a minimal environmental footprint in terms of resource use, energy consumption, and emissions, such as low VOC paints, water-based adhesives, and eco-friendly coatings. Eco-friendly design principles. Eco-friendly design principles focus on minimizing environmental impact, conserving resources, and promoting sustainability throughout the design process. Key principles include life cycle assessment, or LCA. Assessing the environmental impact of a product or material throughout its entire life cycle, from raw material extraction to end-of-life disposal. LCAs help identify opportunities for improvement and inform decision-making. Resource efficiency. Designing products to maximize resource efficiency by minimizing material use, optimizing manufacturing processes, and reducing waste generation. Energy efficiency. Designing products to minimize energy consumption during production, use, and disposal phases. This includes using energy-efficient manufacturing technologies, incorporating renewable energy sources, and designing products for energy-efficient operation. Circular design. Designing products with circularity in mind, aiming to keep materials and resources in use for as long as possible through strategies such as reuse, repair, remanufacturing, and recycling. Biophilic design. Incorporating natural elements and patterns into design to enhance human well-being, connection to nature, and environmental sustainability. Biophilic design principles include integrating natural light, views of nature, indoor plants, and natural materials into built environments. Sustainable packaging. Designing packaging solutions that minimize environmental impact, reduce waste, and promote recyclability or compostability. This includes using recycled and renewable materials, reducing packaging volume and weight, and designing for disassembly. User-centered design. Designing products that meet user needs and preferences while promoting sustainability. This includes considering factors such as product durability, ease of repair, energy efficiency, and end-of-life options. Local sourcing. Sourcing materials and manufacturing locally to reduce transportation-related emissions, support local economies, and promote regional sustainability. Benefits of sustainable materials and eco-friendly design. Environmental protection. Sustainable materials and eco-friendly design practices help reduce resource depletion, pollution, and habitat destruction, contributing to environmental conservation and biodiversity preservation. Resource efficiency. By optimizing resource use and minimizing waste, sustainable materials and design practices help conserve the natural resources and reduce the environmental footprint of products and processes. Cost savings. Adopting sustainable materials and design practices can lead to long-term cost savings through reduced material consumption, energy efficiency improvements, waste reduction, and enhanced brand reputation. Market differentiation. Consumers increasingly value sustainability and environmental responsibility, making products and brands that prioritize eco-friendly design more attractive and competitive in the market. By incorporating sustainable materials and eco-friendly design principles into their practices, industrial designers can create products that not only meet user needs and preferences, but also promote environmental sustainability and contribute to a more sustainable future. 4.4. Prototyping. Methods and best practices. Prototyping stands as a cornerstone of the design process, offering designers the chance to trial and refine their concepts before transitioning to production. Here's an overview of the diverse methods and best practices. Prototyping methods. Paper prototyping. Sketching or printing designs on paper for quick and low-cost concept testing. Digital prototyping. Employing computer software like CAD or 3D modeling for detailed virtual prototypes. 3D printing or additive manufacturing. Building physical prototypes layer by layer from digital designs. CNC machining. Utilizing computer-controlled machines to craft prototypes with high precision. Foam modeling. Carving or shaping foam blocks to visualize and test design form. Prototyping kits. Assembling functional prototypes using pre-made components. Soft prototyping. Utilizing soft materials like fabrics or silicone for tactile testing. Best practices for prototyping. Start early. Initiate prototyping as soon as possible in the design process. Focus on key features. Prioritize prototyping critical design aspects. Iterate often. Continuously prototype, test, and refine designs. Use the right fidelity. Match prototype fidelity to the design stage. Involve stakeholders. Gather feedback from users, clients, and team members. Test real-world conditions. Simulate real-world usage scenarios for testing. Document learnings. Keep track of insights and observations for future reference. Be open to change. Embrace feedback and be willing to adapt designs accordingly. Consider manufacturing constraints. Account for manufacturing feasibility and constraints. Safety first. Ensure safety precautions are taken, especially with machinery and tools. By employing these prototyping methods and best practices, designers can effectively refine their designs, mitigate risks, and create products that meet user needs. Part 5. Problem Solving in Industrial Design. 5.1. Identifying and defining problems. Identifying and defining problems is a crucial step in the design process, setting the foundation for creating innovative and effective solutions. Here's an overview of the process. Observation and research. Begin by observing the context in which the problem exists and conducting thorough research to understand the needs, challenges, and constraints of the stakeholders involved. This may involve interviews, surveys, market analysis, and user observations to gather insights and identify pain points. Define the scope. Clarify the scope of the problem by defining its boundaries and key objectives. This involves articulating the problem statement in a clear and concise manner, focusing on the specific issue that needs to be addressed. Avoid making assumptions and ensure alignment with the goals of the project and the needs of the users. Stakeholder engagement. Involve relevant stakeholders, including end users, clients, domain experts, and other key stakeholders in the problem definition process. Their perspectives and input are valuable for gaining a comprehensive understanding of the problem and ensuring that the solution meets their needs. Problem framing. Frame the problem in a way that inspires creativity and innovation. This involves reframing the problem statement to uncover underlying needs, opportunities, and constraints. Consider alternative perspectives, reframe assumptions, and ask open-ended questions to explore the problem space from different angles. Root cause analysis. Identify the root causes of the problem by analyzing its underlying factors and contributing variables. This may involve using techniques such as root cause analysis, fishbone diagrams, or systems thinking to uncover the root causes of the problem and understand its complexity. Prioritization. Prioritize problems based on their impact, feasibility, and urgency. Not all problems are equally important or solvable within the given constraints. Use criteria such as stakeholder priorities, resource availability, and project timelines to prioritize which problems to address first. Refinement and iteration. Iterate on the problem definition as new insights emerge and the project progresses. Refine the problem statement based on feedback from stakeholders, additional research, and ongoing analysis. Be open to revisiting and adjusting the problem definition as needed to ensure alignment with project goals and user needs. Documentation. Document the problem definition process, including the insights gathered, key findings, and the finalized problem statement. This documentation serves as a reference for the design team and stakeholders throughout the project and provides transparency and accountability in decision-making. By following these steps, designers can effectively identify and define problems, laying the groundwork for developing innovative and impactful solutions that address the needs and aspirations of users and stakeholders. 5.2. Analytical tools and techniques. Analytical tools and techniques are essential resources for understanding data, gaining insights, and making informed decisions across various domains. Here's an overview of some common analytical tools and techniques. Statistical analysis. Statistical analysis involves the use of mathematical techniques to analyze data sets and uncover patterns, trends, and relationships. Common statistical methods include descriptive statistics, summarizing and describing the main features of a dataset, such as mean, median, mode, variance, and standard deviation. Inferential statistics, drawing conclusions and making predictions about a population based on a sample using techniques such as hypothesis testing, regression analysis, and analysis of variance. Data visualization. Data visualization techniques transform raw data into visual representations, such as charts, graphs, and maps, to facilitate understanding and interpretation. Common data visualization tools include charts and graphs, bar charts, line graphs, pie charts, scatter plots, and histograms to represent data in visual formats. Dashboards. Interactive dashboards that display key metrics and trends in real time, allowing users to explore and analyze data dynamically. Geographic information systems. Mapping and spatial analysis tools for visualizing and analyzing geographic data such as demographics, infrastructure, and environmental factors. Machine learning. Machine learning algorithms enable computers to learn from data and make predictions or decisions without explicit programming. Common machine learning techniques include supervised learning, training models on labeled data to make predictions or classify new instances, using algorithms such as linear regression, logistic regression, decision trees, and support vector machines. Unsupervised learning. Identifying patterns and structures in unlabeled data, using techniques such as clustering, e.g. k-means clustering, and dimensionality reduction, e.g. principal component analysis. Deep learning. Neural network-based algorithms that learn complex representations of data, used in tasks such as image recognition, natural language processing, and speech recognition. Qualitative analysis. Qualitative analysis involves examining non-numeric data such as text, images, and videos to identify themes, patterns, and insights. Common qualitative analysis techniques include content analysis, analyzing text or media content to identify recurring themes, sentiment, and patterns. Grounded theory. Developing theories or explanations based on systematic analysis of qualitative data, allowing insights to emerge from the data itself. Ethnography. Immersive observation and study of people and cultures in their natural environment to understand behaviors, beliefs, and practices. Optimization techniques. Optimization techniques aim to find the best solution to a problem within given constraints. Common optimization methods include linear programming, optimizing the allocation of resources to maximize or minimize an objective function subject to linear constraints. Genetic algorithms. Evolutionary algorithms that mimic natural selection to find optimal solutions to complex problems. Simulations. Modeling and simulating real-world systems to optimize processes, improve efficiency, and evaluate alternative scenarios. Decision analysis. Decision analysis techniques help decision makers evaluate alternatives, assess risks, and make optimal decisions under uncertainty. Common decision analysis methods include decision trees, visual representations of decision-making processes, showing possible outcomes and their probabilities. Monte Carlo simulation. Simulating thousands of possible outcomes based on probability distributions to analyze risks and uncertainties in decision-making. Sensitivity analysis. Assessing the impact of changes in variables or assumptions on decision outcomes to identify key drivers and risks. By leveraging these analytical tools and techniques, organizations can extract valuable insights from data, optimize processes, and make data-driven decisions that drive innovation and success. Part 6. User-centered design. 6.1. Ergonomics and human factors. Ergonomics and human factors engineering are disciplines focused on optimizing human performance, safety, and well-being in various environments and interactions. Ergonomics encompasses the study of human body measurements, movements, and capabilities to ensure that products, workspaces, and tools accommodate diverse user needs. It considers factors like anthropometry, biomechanics, and human physiology to design comfortable and efficient environments. Human factors extends beyond ergonomics to include psychological, social, and organizational aspects that influence human behavior and performance. It encompasses cognitive ergonomics, user experience design, safety engineering, and human-computer interaction, aiming to create intuitive and user-friendly systems. Both disciplines find applications in industries such as manufacturing, healthcare, transportation, consumer products, and information technology. By integrating principles of ergonomics and human factors into design processes, professionals can create products, systems, and environments that enhance user satisfaction, productivity, and safety. 6.2. User experience and interaction design. User experience design and interaction design are integral aspects of creating products and services that meet user needs and expectations. User experience design focuses on understanding users' behaviors, needs, and motivations to create seamless and satisfying experiences. It encompasses a holistic approach to design, considering all aspects of a user's interaction with a product or service. This includes factors such as usability, accessibility, aesthetics, and emotional appeal. User experience designers conduct user research, create user personas, design wireframes and prototypes, and iterate on designs based on user feedback to ensure a positive user experience. Interaction design, on the other hand, specifically focuses on designing the interaction between users and digital interfaces. It involves designing the layout, structure, and behavior of interactive elements such as buttons, menus, and navigation systems to facilitate intuitive and efficient user interactions. Interaction designers use principles of usability, information architecture, and visual design to create interfaces that are easy to use and understand. Together, user experience design and interaction design play a crucial role in shaping the overall user experience of products and services. By applying user-centered design principles, conducting usability testing, and iterating on designs based on user feedback, designers can create intuitive, engaging, and user-friendly experiences that meet the needs and expectations of users. 6.3. Inclusive design and accessibility. Inclusive design and accessibility focus on creating products, services, and environments that are usable and accessible to people of all abilities and backgrounds. Inclusive design goes beyond traditional accessibility by considering the diverse needs, preferences, and abilities of all users. It aims to design products and experiences that are inherently inclusive, rather than retrofitting them for specific user groups. Inclusive design principles emphasize flexibility, diversity, and user empowerment, ensuring that everyone can participate fully and independently. This approach benefits not only people with disabilities, but also older adults, children, and individuals with temporary or situational limitations. Accessibility, on the other hand, specifically addresses barriers faced by people with disabilities in accessing and using products, services, and environments. This includes physical disabilities, sensory impairments, such as vision or hearing loss, cognitive disabilities, and mobility limitations. Accessibility considerations may involve providing alternative formats, assistive technologies, and accommodations to ensure equal access and participation for people with disabilities. Both inclusive design and accessibility are guided by principles of equity, dignity, and social responsibility. By incorporating inclusive design and accessibility principles into the design process, designers can create products and experiences that are usable, equitable, and empowering for all users. This not only enhances the user experience, but also contributes to a more inclusive and equitable society. 6.4. User testing and feedback. User testing and feedback play pivotal roles in the design process, providing designers with invaluable insights into how users interact with products and services. These insights are crucial for making informed decisions and refining designs to better meet user needs and expectations. User testing involves observing real users as they interact with prototypes or existing products. This process helps identify usability issues, gather feedback, and validate design decisions. Usability testing, for instance, allows designers to observe users performing specific tasks with a prototype or product, highlighting areas of difficulty or confusion. Similarly, prototype testing enables designers to gather feedback on early-stage designs, validating concepts, features, and user flows before finalizing designs. Beta testing involves releasing a product to a limited group of users in real-world conditions, gathering feedback on performance, reliability, and user experience. A or B testing compares different variations of a design or feature to determine which performs better in terms of user engagement or conversion rates. Remote testing, on the other hand, allows for user testing sessions to be conducted remotely, reaching a broader audience and gathering feedback from diverse user groups. User feedback, meanwhile, involves soliciting input from users through surveys, interviews, focus groups, or feedback forms. This feedback helps designers understand user needs, preferences, and pain points. Open-ended questions encourage users to share their experiences, opinions, and suggestions in their own words. Closed-ended questions provide quantitative data on user preferences and satisfaction. Contextual inquiry involves observing users in their natural environment to understand how they use products or services and identify unmet needs or workflow challenges. Surveys and polls collect feedback from a larger audience, using structured questions to gather quantitative data on user satisfaction, usability, and feature preferences. Feedback loops within products or services, such as feedback forms or rating systems, enable users to provide feedback directly within the user interface. By incorporating user testing and feedback into the design process, designers gain valuable insights into user needs and behaviors. This enables them to validate design decisions, prioritize features, and identify opportunities for improvements. Ultimately, user testing and feedback are essential for creating products and experiences that meet user expectations, drive user satisfaction, and foster long-term success. Part 7. Digital Tools and Technologies. 7.1. Computer-Aided Design, or CAD, software. Computer-Aided Design software, or CAD software, revolutionizes the design process by enabling engineers, architects, and designers to create precise and detailed 2D and 3D models of objects, buildings, and mechanical components. CAD software offers a wide range of tools and features to streamline the design process, improve accuracy, and enhance collaboration. CAD software allows users to create, modify, analyze, and visualize designs with ease. Here are some key features and benefits of CAD software. Key features: 2D drafting. CAD software provides tools for creating accurate 2D drawings, including lines, arcs, circles, and text. 3D modeling. Users can create detailed 3D models of objects and structures using solid modeling, surface modeling, and parametric modeling techniques. Parametric design. Parametric modeling allows users to define geometric relationships and constraints, making it easy to modify designs and maintain design intent. Assembly design. CAD software enables users to create complex assemblies of components, simulate motion, and detect interference or collisions. Visualization. CAD software provides tools for rendering and visualizing designs in photorealistic detail, helping users communicate their ideas effectively. Analysis. Some CAD software includes analysis tools for performing simulations such as stress analysis, thermal analysis, and fluid flow analysis. Collaboration. CAD software facilitates collaboration between team members by allowing multiple users to work on the same project simultaneously and providing tools for version control and file sharing. Customization. Many CAD software packages are highly customizable, allowing users to create custom commands, scripts, and templates to streamline their workflows. Benefits. Improved efficiency. CAD software streamlines the design process, reducing the time and effort required to create and modify designs. Higher accuracy. CAD software enables users to create precise and detailed designs, minimizing errors and inconsistencies. Enhanced visualization. CAD software provides tools for visualizing designs in 2D and 3D, helping users to better understand and communicate their ideas. Better collaboration. CAD software facilitates collaboration between team members, allowing for real-time collaboration and easy sharing of design files. Cost savings. CAD software reduces the need for physical prototypes and allows for virtual testing and simulation, saving time and money in the design process. Innovation. CAD software empowers designers to explore new ideas and concepts, enabling innovation and creativity in design. Overall, CAD software is a powerful tool that revolutionizes the design process, empowering users to create accurate, detailed, and innovative designs in a collaborative and efficient manner. 7.2 3D Modeling and Simulation. In the realm of design and engineering, 3D modeling and simulation stand as transformative technologies, reshaping the way we visualize, analyze, and optimize complex systems and designs. 3D modeling. At its core, 3D modeling involves the creation of digital representations of objects or environments in 3 dimensions. This process encompasses a range of techniques. Solid modeling allows for the creation of intricate models using geometric primitives, which can be manipulated to form complex shapes. Surface modeling, on the other hand, focuses on creating smooth and organic shapes using surfaces and curves. Parametric modeling enables designers to define relationships and constraints between elements, facilitating easy modification and maintenance of design integrity. Additionally, mesh modeling is common in computer graphics and animation, enabling the creation of characters and environments through vertices, edges, and faces. Moreover, through scanning and reconstruction technologies, real-world objects and environments can be digitized for analysis and visualization. Applications of 3D modeling. The applications of 3D modeling are vast and varied. In product design and manufacturing, digital prototypes streamline the design process, optimizing products for manufacturing and simulating assembly processes. In architecture and construction, detailed building models allow for the visualization of architectural designs and the simulation of construction processes to identify potential issues. Entertainment and media industries leverage 3D modeling for creating characters, environments, and visual effects in video games, movies, and animations. Furthermore, in medical and healthcare fields, 3D models aid in surgical planning, medical education, and the visualization of medical data. Geospatial analysis benefits from 3D models of landscapes, terrain, and urban environments, supporting urban planning, environmental analysis, and geographic information systems. Simulation. Simulation involves the use of computer models to replicate the behavior of real-world systems, enabling analysis under various conditions. This encompasses several key areas. Finite element analysis, or FEA, simulates the behavior of structures and mechanical components to predict stress, deformation, and failure. Computational fluid dynamics simulates fluid flow and heat transfer in systems such as airflow around buildings or aerodynamics of vehicles. Multi-body dynamics models the motion and interactions of interconnected bodies in mechanical systems, including vehicles, machinery, and robotics. Electromagnetic simulation analyzes electromagnetic fields and interactions in electronic devices, antennas, and electric machines. Applications of simulation. Simulation finds applications across numerous domains. In engineering design and analysis, Simulations optimize product designs, identify issues, and validate performance before physical prototyping. Safety and risk analysis assesses the reliability of systems, predicts failure modes, and evaluates the impact of design changes. Process optimization analyzes and refines manufacturing processes, supply chain logistics, and operational workflows. Training and education benefit from virtual simulations, providing safe and controlled environments for training operators, pilots, and medical professionals. In essence, 3D modeling and simulation are indispensable tools, empowering designers and engineers to innovate, optimize, and mitigate risks across a wide array of industries. By harnessing these technologies, organizations can drive efficiency, foster innovation, and maintain competitiveness in today's rapidly evolving landscape of design and engineering. 7.3. Virtual reality, or VR, and augmented reality, or AR, in design. Virtual reality and augmented reality have ushered in a new era for design, offering immersive and interactive experiences that redefine how designers visualize, prototype, and evaluate their creations. These cutting-edge technologies seamlessly blend the digital and physical worlds, providing users with unprecedented capabilities to interact with virtual objects and environments in real time. Let's delve into how VR and AR are reshaping the landscape of design. Virtual reality, or VR. VR immerses users in fully digital environments, accessed through headsets or other devices. Here's how VR is revolutionizing design. Immersive visualization. VR provides designers with a three-dimensional canvas to visualize their creations, offering insights into scale, depth, and spatial relationships that traditional 2D representations cannot match. Virtual prototyping. Designers can rapidly iterate and refine their designs by creating and testing virtual prototypes before investing in physical models, saving time and resources in the design process. Simulation and training. VR simulations replicate real-world scenarios, allowing users to practice skills, conduct training sessions, or simulate complex processes in a safe and controlled environment. Collaborative design. VR platforms facilitate real-time collaboration among multiple users in virtual environments, enabling seamless communication, feedback, and decision-making regardless of physical location. Augmented reality, or AR. AR overlays digital information onto the physical world, enhancing users' perception of reality. Here's how AR is transforming design. Spatial context. AR overlays digital content onto physical objects or environments, providing contextual information and enhancing understanding of spatial relationships. Visualization and annotation. Designers can visualize and annotate designs in real-world contexts, allowing for on-site evaluations, feedback, and decision-making. Remote assistance. AR enables remote experts to provide guidance and support to users in real time, using annotations, instructions, or visual cues overlaid onto the user's view. Product visualization. AR apps allow users to visualize products in their own space before making purchasing decisions, enhancing the online shopping experience and reducing the need for physical stores. Applications of VR and AR in design. Architecture and construction. Architects and builders leverage VR and AR to visualize designs, simulate construction processes, and conduct virtual walkthroughs of buildings before construction begins. Product design and manufacturing. Designers use VR and AR to create and test prototypes, visualize assembly processes, and optimize product designs for manufacturing. Interior design and retail. Interior designers and retailers utilize VR and AR to create virtual showrooms, visualize furniture and decor in real-world spaces, and provide immersive shopping experiences to customers. Urban planning and landscape design. VR and AR tools facilitate urban planning and landscape design by visualizing proposed developments, simulating traffic patterns, and assessing environmental impacts. VR and AR technologies are reshaping the design process, providing designers with powerful tools for visualization, prototyping, and collaboration. By harnessing the capabilities of VR and AR, designers can create more immersive, engaging, and innovative experiences, ultimately leading to better informed decisions and more successful designs. 7.4. Rapid prototyping and 3D printing. In the realm of design and engineering, rapid prototyping and 3D printing have emerged as game-changing technologies, reshaping the traditional approach to creating prototypes and manufacturing processes. These innovations offer designers and engineers unparalleled speed, flexibility, and cost-effectiveness in transforming digital designs into physical objects. Let's delve into how rapid prototyping and 3D printing are revolutionizing the design and manufacturing landscape. Rapid prototyping. Rapid prototyping is a process that involves quickly creating physical prototypes of a design to test its functionality, form, and usability. It offers several advantages. Speed. Rapid prototyping technologies drastically reduce the time required to create physical prototypes compared to traditional manufacturing methods. This acceleration enables designers to iterate rapidly and refine designs in a fraction of the time it would take using conventional approaches. Cost effectiveness. By eliminating the need for expensive tooling and machining processes, rapid prototyping significantly reduces the cost associated with creating prototypes. This cost effectiveness makes it accessible to designers, entrepreneurs, and small businesses leveling the playing field in product development. Flexibility. Rapid prototyping supports a wide range of materials and fabrication methods, allowing designers to create prototypes with diverse properties, textures, and finishes. This versatility enables designers to explore different design iterations and material options to achieve the desired outcome. Iterative design. Rapid prototyping facilitates an iterative design process, where designers can quickly test and refine multiple design iterations based on user feedback and performance testing. This iterative approach leads to better designed products that meet user needs and expectations. 3D printing. 3D printing, also known as additive manufacturing, is a process that builds objects layer by layer from digital 3D models. It offers several unique capabilities. Versatility. 3D printing supports a wide range of materials, including plastics, metals, ceramics, and composites, offering designers flexibility in material selection for different applications. This versatility enables the production of parts with varying mechanical, thermal, and aesthetic properties to meet specific requirements. Complex geometry. Unlike traditional manufacturing methods, which are limited by the constraints of machining processes, 3D printing enables the creation of complex geometric shapes and intricate designs with ease. This capability unlocks new possibilities in design, allowing designers to explore innovative shapes and structures that were previously unattainable. Customization. 3D printing enables mass customization, where each part can be tailored to meet specific requirements or personalized to individual preferences. This customization capability is particularly valuable in industries such as healthcare, where customized medical implants and prosthetics can improve patient outcomes and quality of life. On-demand manufacturing. 3D printing enables on-demand production, reducing the speed for large inventories and enabling just-in-time manufacturing and localized production. This flexibility helps businesses optimize inventory management, reduce storage costs, and respond quickly to changes in demand. Applications. Rapid prototyping and 3D printing find applications across various industries and domains. Product development. These technologies are widely used in product development to create prototypes for testing, validation, and user feedback. They enable designers to iterate quickly and efficiently, accelerating the product development process and reducing time to market. Custom manufacturing. 3D printing enables the production of custom parts and products tailored to individual customers' needs. From personalized consumer goods to customized medical implants, 3D printing offers unparalleled flexibility in manufacturing. Tooling and jigs. Rapid prototyping and 3D printing are used to create tooling, fixtures, and jigs for manufacturing processes. These custom-made tools improve efficiency and accuracy in production, leading to cost savings and improved product quality. Education and research. Rapid prototyping and 3D printing are valuable tools in education and research, allowing students and researchers to explore concepts, visualize ideas, and create prototypes for experimentation and testing. They promote hands-on learning and facilitate innovation in various fields. Rapid prototyping and 3D printing have transformed the design and manufacturing landscape, offering designers and engineers unprecedented capabilities to innovate, iterate, and customize products. By leveraging these technologies, businesses can accelerate product development, reduce costs, and stay competitive in today's fast-paced and dynamic market. As rapid prototyping and 3D printing continue to evolve, their impact on design and manufacturing will only grow, unlocking new opportunities for creativity, efficiency, and sustainability. Part 8. Project Management and Collaboration. 8.1. Managing Design Projects. Managing design projects is a multifaceted endeavor that requires a delicate balance of creativity, organization, and effective communication. At its core, successful project management in the realm of design hinges on several key principles and strategies aimed at guiding teams toward achieving their goals and delivering exceptional outcomes. Defining project objectives. Before embarking on any design project, it is imperative to establish clear objectives and parameters. This involves collaborating with stakeholders to define the project's scope, goals, and deliverables. Understanding user needs is also crucial, as it informs design decisions and shapes project requirements. Planning and organization. Once project objectives are defined, meticulous planning and organization are essential for success. A detailed project plan should be developed, outlining tasks, milestones, timelines, and resource allocation. Prioritizing activities ensures that critical tasks are addressed first, while proper resource allocation involves assigning roles and responsibilities to team members based on their skills and expertise. Fostering collaboration. Effective collaboration lies at the heart of successful design project management. Encouraging cross-functional collaboration between designers, developers, marketers, and other stakeholders fosters the exchange of ideas and perspectives. Clear communication channels should be established to facilitate the sharing of ideas, feedback, and updates throughout the project lifecycle. Leveraging collaboration tools such as project management software and communication platforms streamlines collaboration and enhances document sharing. Managing risk. Anticipating and mitigating risks are integral aspects of project management. Identifying potential risks and challenges allows project managers to develop proactive mitigation strategies. Monitoring project progress against milestones and objectives enables timely identification of deviations from the plan, allowing for corrective action to be taken as necessary. Flexibility and adaptability are key in responding to changes in project requirements, timelines, or scope. Ensuring quality. Maintaining design standards and guidelines is essential for ensuring consistency and quality across project deliverables. Regular design reviews and feedback sessions with stakeholders facilitate the evaluation of progress and the incorporation of feedback into design iterations. Usability testing and iteration cycles enable refinement of designs based on user feedback, ensuring that final deliverables meet user needs and expectations. Evaluating and learning. After project completion, reflection and evaluation are vital for learning and improvement. Conducting project postmortems allows teams to reflect on successes, challenges, and lessons learned, identifying areas for improvement in future projects. Gathering feedback from stakeholders and team members provides insights into project performance and opportunities for process refinement and optimization. Continuous improvement is fostered through the application of insights gleaned from project evaluations to refine project management processes, tools, and techniques. In conclusion, effective project management in design requires a holistic approach that encompasses planning, organization, collaboration, risk management, quality assurance, evaluation, and learning. By adhering to these principles and strategies, project managers can lead their teams towards successful project outcomes that meet user needs and business objectives. 8.2. Collaborative design. Working with teams and stakeholders. Collaborative design stands as a cornerstone in the realm of successful projects, necessitating effective teamwork and stakeholder engagement throughout the design process. Its significance lies in embracing diverse perspectives, establishing communication channels, involving stakeholders, resolving conflicts constructively, and celebrating achievements. Let's delve deeper into the essence of collaborative design and its implications for working with teams and stakeholders. Embracing diverse perspectives. In collaborative design, diversity of thought is celebrated. By encouraging cross-functional collaboration, teams can leverage the expertise and insights of individuals from various disciplines such as design, development, marketing, and more. Additionally, adopting a user-centric approach ensures that designs are informed by user needs and preferences, with stakeholders providing valuable feedback to ensure alignment with user expectations. Establishing communication channels. Effective communication is vital for the success of collaborative design projects. Teams must foster an environment of open communication where ideas, feedback, and concerns can be freely shared among team members and stakeholders. Regular check-in meetings or stand-ups help keep everyone informed, allowing for updates, addressing challenges, and aligning on priorities in a timely manner. Utilizing collaboration tools. The use of collaboration tools further facilitates effective teamwork. Project management software enables teams to track tasks, milestones, and deadlines, promoting transparency and accountability. Communication platforms such as Slack or Microsoft Teams facilitate real-time communication and file sharing, enhancing collaboration among team members regardless of geographical location. Involving stakeholders. Stakeholder engagement is integral to the success of collaborative design projects. Involving stakeholders early and consistently throughout the design process ensures that designs meet business objectives and user needs. User testing sessions and feedback gathering provide valuable insights, allowing teams to validate design decisions and iterate based on user feedback. Resolving conflicts. Conflict resolution is a natural part of collaborative work. Teams must address conflicts promptly and constructively, seeking compromise and consensus to move the project forward. Active listening and empathy play crucial roles in resolving disagreements, fostering a culture of respect and collaboration within a team. Celebrating achievements. Recognition of team achievements is essential for maintaining morale and motivation. Celebrating milestones and acknowledging the contributions of team members and stakeholders fosters a positive team dynamic and encourages continued collaboration. Additionally, reflecting on successes and challenges helps identify areas for improvement, driving continuous growth and development in collaborative design practices. In conclusion, collaborative design is instrumental in driving innovation, fostering creativity, and delivering successful outcomes in design projects. By embracing diverse perspectives, establishing effective communication channels, involving stakeholders, resolving conflicts constructively, and celebrating achievements, teams can harness collective expertise to create impactful and user-centric designs. 8.3 Communication and presentation skills for designers. Communication and presentation skills are vital components of a designer's toolkit, essential for effectively conveying ideas, collaborating with team members, and advocating for design solutions. Let's delve into the significance of these skills and their implications for designers. Articulating design concepts. Designers must master the art of articulating their ideas with clarity and precision. By communicating their concepts clearly and concisely, designers can ensure that their vision is understood by both technical and non-technical audiences. Visual aids such as sketches, wireframes, and prototypes play a crucial role in supplementing verbal explanations and helping convey design concepts more effectively. Collaborating with team members. Effective communication is key to successful collaboration within design teams. Designers must cultivate active listening skills, attentively considering feedback and ideas from team members. Providing constructive feedback in return fosters a supportive environment where all team members feel valued and heard, contributing to a culture of creativity and innovation. Engaging with stakeholders. Engagement with stakeholders is a fundamental aspect of the design process. Designers must adapt their communication and presentation styles to resonate with different audiences, whether they are clients, executives, or end users. Employing storytelling techniques helps create compelling narratives that illustrate the value and impact of design solutions, fostering greater buy-in and support from stakeholders. Presenting design work. Effective presentation skills are essential for showcasing design work in a compelling and persuasive manner. Thorough preparation is key, involving the organization of key points, practice of delivery, and anticipation of potential questions or objectives. Visual design plays a crucial role in presentations, with designers using typography, color, and layout to enhance clarity and engagement and create memorable presentations. Soliciting and incorporating feedback. Receiving and incorporating feedback is an integral part of the design process. Designers must approach feedback with an open mind, viewing it as an opportunity for growth and improvement rather than criticism. Adopting an iterative approach to design allows designers to refine and enhance their solutions over time, incorporating feedback from stakeholders and users to create more impactful and successful designs. Handling questions and challenges. Confidence and problem-solving skills are essential when facing questions and challenges during presentations. Designers must maintain confidence in presenting their work, remaining composed and assured even in the face of difficult questions or critiques. Demonstrating problem-solving skills by addressing questions thoughtfully and collaboratively, drawing on relevant evidence and expertise, helps build credibility and trust with stakeholders. So, communication and presentation skills are indispensable for designers, enabling them to effectively convey ideas, collaborate with team members, engage stakeholders, and advocate for design solutions. By honing these skills, designers can enhance their ability to articulate their vision, foster collaboration, and ultimately create impactful and successful design solutions. 8.4. Intellectual property and patents. Intellectual property and patents serve as crucial safeguards for designers and innovators, ensuring the protection of their creations and inventions from unauthorized use or replication. In the design industry, these legal mechanisms play a pivotal role in securing the rights and interests of individuals and companies alike. Understanding intellectual property protection. Intellectual property encompasses a broad spectrum of creations of the mind, including inventions, designs, literary and artistic works, and commercial symbols. Within this framework, various forms of protection exist, including patents, trademarks, copyrights, and trade secrets. each offers distinct avenues for shielding creative and innovative endeavors from infringement. Delving into patents in design. At the heart of intellectual property protection for designers lies the concept of patents. A patent is a legal right granted by a government to an inventor, bestowing exclusive rights to their invention for a defined period, typically 20 years from the filing date. For designers, patents specifically safeguard the ornamental design or appearance of a functional item, granting exclusive rights to utilize, produce, market, or import the design. The significance of patents for designers. For designers, patents represent more than just legal protections. They serve as invaluable tools for safeguarding design innovations. By securing patents for their creative designs, designers can prevent unauthorized replication or imitation, preserving their competitive edge in the market. Moreover, patented designs enable designers to establish unique selling propositions, setting their products apart from competitors and enhancing brand recognition and loyalty. Navigating the patent process. Obtaining a patent involves a comprehensive process, beginning with the submission of a patent application to the relevant patent office. This application entails detailed descriptions, drawings, and claims outlining the invention's novelty, non-obviousness, and utility. Subsequently, the Patent Office conducts an examination to assess the applicant's merits. Upon meeting the necessary criteria, the patent is granted, affording legal protection to the inventor's design. Enforcement and global considerations. Once granted, patent holders must diligently monitor the marketplace for potential infringements and take appropriate legal action against unauthorized use or replication. This may involve issuing cease and desist letters, negotiating licensing agreements, or pursuing litigation to safeguard their rights. Additionally, designers seeking international protection for their designs can leverage international treaties and conventions, such as the Paris Convention and the Patent Cooperation Treaty, to secure patents in multiple countries or regions. Part 9. Trends and Future Directions. 9.1. Emerging Trends in Industrial Design. Industrial design, a field at the intersection of art, engineering, and innovation, is constantly evolving to meet the changing needs and preferences of consumers, as well as advancements in technology and materials. Here's an exploration of some emerging trends shaping the landscape of industrial design. Sustainable design. With growing concerns about environmental sustainability, there is a heightened emphasis on incorporating sustainable practices and materials into industrial design. Designers are exploring eco-friendly materials, energy-efficient manufacturing processes, and product lifecycle considerations to minimize environmental impact. Human-centered design. Human-centered design puts people at the center of the design process, prioritizing user needs, preferences, and experiences. Designers are increasingly focusing on creating products that are intuitive, accessible, and inclusive, with a keen understanding of user behavior and psychology. Digitalization and smart products. Advancements in digital technology and the Internet of Things are driving the emergence of smart products and connected ecosystems. Industrial designers are integrating sensors, connectivity, and data analytics into products to enhance functionality, provide personalized experiences, and enable new forms of interaction. Customization and personalization. Consumers are seeking products that reflect their individual tastes and preferences, leading to a rise in customization and personalization in industrial design. Designers are leveraging technologies such as 3D printing and digital fabrication to offer bespoke solutions tailored to each customer's needs. Circular economy and product lifecycle. The shift towards a circular economy model is influencing industrial design practices, with an emphasis on designing products for longevity, repairability, and recyclability. Designers are exploring strategies such as modular design, material recovery, and product-as-a-service models to minimize waste and promote resource efficiency. Biomimicry and nature-inspired design. Biomimicry, or nature-inspired design, draws inspiration from the natural world to solve complex design challenges. Industrial designers are studying biological systems, structures, and processes to create products that are more efficient, sustainable, and resilient. Minimalism and simplicity. In response to information overload and sensory overload, there is a growing trend towards minimalism and simplicity in industrial design. Designers are embracing clean lines, minimalist aesthetics, and intuitive interfaces to create products that are visually appealing and easy to use. Collaborative and co-creative design. Collaboration is becoming increasingly central to the design process, with designers working closely with cross-disciplinary teams, stakeholders, and end users to co-create solutions. Design thinking methodologies and participatory design approaches are being employed to foster creativity, empathy, and innovation. As industrial design continues to evolve, driven by changing consumer expectations, technological advancements, and societal trends, designers must stay abreast of emerging trends and embrace a spirit of innovation and adaptability. By harnessing the potential of sustainability, human-centered design, digitalization, customization, circular economy principles, biomimicry, minimalism, and collaboration, designers can create products that resonate with users, enhance quality of life, and contribute to a more sustainable and inclusive future. 9.2. The impact of technology on design. Technology has fundamentally reshaped the landscape of design, ushering in a new era of innovation and creativity across various domains. From the tools and software designers use to the way they collaborate, communicate, and manufacture products, technology has permeated every aspect of the design process. In the realm of design tools and software, the emergence of digital design software like Adobe Creative Suite, Sketch, and Autodesk has empowered designers with unparalleled capabilities for creating and manipulating digital assets. These tools have revolutionized the way designers conceptualize and execute their ideas, enabling them to bring their visions to life with precision and efficiency. Similarly, advancements in computer-aided design, or CAD software, have revolutionized the design process, allowing designers to create intricate technical drawings, schematics, and prototypes with remarkable speed and accuracy. With CAD technology, designers can iterate on designs more quickly, explore alternative solutions, and refine their ideas with greater precision than ever before. Technology has also transformed the way designers collaborate and communicate, particularly in an era of remote work and global teams. Collaboration tools such as Slack, Microsoft Teams, and Zoom have become indispensable for facilitating communication, file sharing, and real-time collaboration among designers and team members, regardless of geographical location. Moreover, virtual reality, or VR, and augmented reality, or AR technologies have opened up new possibilities for designers, allowing them to create immersive experiences, visualize designs in real-world contexts, and collaborate with stakeholders in virtual environments. These technologies enable designers to prototype and iterate on designs in a more intuitive and immersive manner, enhancing the overall design process and fostering greater creativity and innovation. In manufacturing and production, technology has also had a profound impact, particularly with the advent of 3D printing and computer numerical control, or CNC, machining. 3D printing technology has revolutionized manufacturing processes, enabling designers to rapidly prototype and produce custom parts and products with complex geometries and materials that were previously unattainable with traditional methods. Furthermore, technology has played a crucial role in advancing sustainability and minimizing the environmental impact of design. Life cycle assessment software allows designers to assess the environmental impact of products throughout their life cycle, from raw material extraction to disposal, enabling them to make informed decisions and optimize designs for sustainability. Additionally, advancements in materials science are driving the development of sustainable materials and manufacturing processes, enabling designers to create products that minimize environmental impact and promote circular economy principles. 9.3. Design for sustainability and the circular economy. Design for sustainability and the circular economy are becoming increasingly prominent concepts in the world of design, reflecting a growing awareness of environmental challenges and the need for more responsible approaches to product design and manufacturing. These principles are reshaping the way designers conceptualize, create, and bring products to market, with a focus on minimizing environmental impact, conserving resources, and promoting a more regenerative and resilient economy. At its core, sustainability in design involves minimizing the environmental footprint of products throughout their entire life cycle, from raw material extraction and production to use and disposal. This requires optimizing resource use, reducing waste, and minimizing energy consumption in the manufacturing process. Additionally, designers are embracing principles of the circular economy, which prioritize strategies such as reducing material use, reusing products and materials, and recycling waste into new products. Designers employ a variety of strategies to promote sustainability and circularity in their work. One approach is through thoughtful material selection, choosing materials that are renewable, biodegradable, or recyclable, as well as those with lower environmental impact and carbon footprint. Designing products for durability, repairability, and upgradability is another key strategy for extending their lifespan and reducing the need for premature replacement. Furthermore, designing products for disassembly facilitates easy separation of components and materials at the end of their life, enabling efficient recycling and reuse of materials in new products. Drawing inspiration from nature through biomimicry and nature-inspired design principles allows designers to leverage the efficiency, resilience, and sustainability observed in natural systems. Collaborative and open-source design approaches are also gaining traction, promoting knowledge sharing, innovation, and collective problem-solving. By embracing principles of sustainability, adopting circular economy strategies, and integrating environmental considerations into every stage of the design process, designers can play a pivotal role in creating a more sustainable and equitable future for all. In essence, design for sustainability and the circular economy represents a fundamental shift in the way design is approached, emphasizing the importance of environmental stewardship, resource conservation, and social responsibility. By incorporating these principles into their work, designers have the opportunity to drive positive change and contribute to a more sustainable and resilient world. 9.4. The future of industrial design. Challenges and opportunities. The future of industrial design presents a landscape rich with both challenges and opportunities, shaped by technological advancements, societal shifts, and environmental imperatives. Challenges. One significant challenge facing industrial designers is the need to navigate an increasingly complex and interconnected global marketplace. Rapid technological innovation and digital disruption are reshaping industries and consumer behaviors, requiring designers to stay abreast of emerging trends and adapt their practices accordingly. Moreover, environmental sustainability is a pressing concern, with resource depletion posing existential threats to our planet. Industrial designers must grapple with the environmental impact of their creations, striving to minimize waste, conserve resources, and promote circular economy principles. Additionally, as products become more interconnected and technology-driven, issues related to data privacy, cybersecurity, and ethical design practices come to the forefront. Designers must prioritize user trust and safety, ensuring that their creations enhance rather than compromise the well-being of individuals and society as a whole. Opportunities. Despite these challenges, the future of industrial design is rife with opportunities for innovation and creativity. Technological advancements such as artificial intelligence, augmented reality, and 3D printing offer new avenues for design exploration, enabling designers to create more personalized, immersive, and sustainable products and experiences. Furthermore, the rise of collaborative and interdisciplinary approaches to design presents exciting opportunities for designers to collaborate with experts from diverse fields, including engineering, biology, and social sciences. By harnessing collective expertise and perspectives, designers can tackle complex challenges and develop innovative solutions that address the needs and aspirations of a diverse global population. Moreover, the growing emphasis on sustainability and social responsibility presents an opportunity for designers to lead the charge towards a more sustainable and equitable future. By integrating environmental considerations into every stage of the design process, designers can create products that minimize environmental impact, promote social equity, and enhance quality of life for all. Conclusion. In conclusion, industrial design stands at a pivotal juncture, poised to address the challenges and opportunities of the future with innovation, creativity, and commitment to sustainability and social responsibility. As technological advancements continue to reshape industries and consumer behaviors, designers must adapt their practices to meet the evolving needs of society while minimizing environmental impacts. By embracing collaborative approaches, leveraging emerging technologies, and integrating principles of sustainability and circular economy into their work, designers can create products and experiences that enhance quality of life, promote equity, and contribute to a more sustainable and resilient future for all. As stewards of creativity and innovation, industrial designers have a unique opportunity to shape the world around us, inspiring positive change and leaving a lasting impact on generations to come. With vision, passion, and a dedication to excellence, the future of industrial design holds boundless possibilities for those willing to embrace the challenges and seize the opportunities that lie ahead.